everyone once again. I welcome you to the second talk of this series at the Center for Atmospheric and Climate Sciences here at IIT Madras. Today's speaker is special in many ways, right? And one of the reasons that why it is special for me is we both have witnessed each other that how we are evolved as the scientists, right? And then not only the scientists, but particularly the aerosol scientists, right? How we started with a different direction and then went on to do the things which are now are common as far as the aerosol cloud interaction is concerned. My association with Vijay dates back to probably our master's days like 2003, 2004, where we were in the Indian Institute of Tropical Meteorology, where I was doing my PhD, and then he did his MTech project there. And then we have been at various places, and then eventually landed up collaborating again on multiple aspects. As far as Vijay is concerned, I don't think so that I should be wasting everyone's time giving the elaborated introduction for it. But then the Vijay Kanawade is now synonymous in India with the new particle formation, right? You as an aerosol scientist obviously know it. Although I'm not a new particle formation expert, but what I know for sure is that as far as the climate impact is concerned of the aerosol, while we have made an immense amount of progress that how do we do, particularly experiment, I'm not talking about the modeling, the new particle formation, particularly the nucleation, it still remains as a big challenge associated with that. I have sent an email outlining his achievements, like have published reputed papers in reputed peer-reviewed journals, very high citations, high citation index, H index. You name any metrics, and then he qualifies on that. Also received numerous awards on various occasions. It's my privilege then to hand it over this to Vijay, and then I'm looking forward to understand and learn more every time I listen to him about the aerosol new particle formation and nucleation. Over to you, Vijay.
Yeah, thank you, Sachin, for the nice introduction and for introducing the topic as well. So that makes my life more easier, and I also get a confidence that I'm not talking to engineers, because I'm not from an engineer background. So yeah, thanks Sachin again for the invite and having me here and to talk about the topic that I love talking about. And I have been working on new particle formation past about 7.5 years. I mean, I have worked previously also, but since I moved to India, my focus was mainly looking at how do we quantify or how do we characterize new particle formation, which is something was unexplored in Indian context. So that's what I will be talking about today. So this will be my talk outline. I'll just briefly introduce what are aerosols. I don't think I have to introduce, but I'll keep it very short, and their implications for weather and climate. Then my focus will be mainly on aerosol dynamics. So I'll try to give some fundamentals of aerosol dynamics, nucleation, condensation, growth, and what exactly makes new particle formation. Then how do we characterize and detect new particle formation, and a bit about there is not much actually work done in Indian context as such, but I will talk about the work that have been done over the last maybe 10-15 years, and what are the recent developments that we have done in this particular field over the last 6-7 years. And then of course we have several knowledge gaps in new particle formation, especially in Indian context, that I will talk about, and what are the multi-institutional efforts that we have been putting, or what are the future direction that one need to to focus on in order to address this very important aspect of aerosol science in general. Yeah, I have a disclaimer here. It's going to be a technical talk with some fundamentals of aerosol dynamics. So aerosols are nothing but the solid or liquid particles in the air, and they have a wide range of size, with about 4 or 5 order of magnitude difference between the smallest and the largest, because I myself consider 20 micrometer particle as a smallest cloud droplet. So I am talking about 1 nanometer to about 10 micrometer. So that is about 4 to 5 orders of magnitude difference. If there is no aerosol, there is no cloud, there is no rain. So it's because the homogeneous nucleation of water vapor is very rare in the atmosphere, for which it requires supersaturation of 200%, which is not there anyway. So you need aerosol in order for a cloud to form and eventually the rainfall. And of course, there are three well-known aerosol effects. I will not talk about that: direct, indirect, and semi-direct. But all these effects are very much dependent on the number of particles, number concentration, their mass, their size, and the composition, right? And that's what it makes very difficult to quantify aerosols' impact on the climate, okay? Which is something, if you take the, let's say, Indian context, we have a strong spatial, temporal heterogeneity across India, whether it's, in terms of number or in terms of a mass or whether in terms of a chemical composition, from the dust to black carbon aerosol and so on. So there are two types of aerosols, primary aerosols and secondary aerosols. Primary aerosols are those which are directly emitted to the atmosphere from various sources, could be natural or anthropogenic. And the secondary aerosols which are formed in the atmosphere either by co-emitted precursor gases condensation onto the pre-existing particles or by vapors nucleating and forming new or fresh particles in the atmosphere, what we call as a aerosol nucleation. So my talk will be mostly, focusing on gas to particle conversion, or what we call as a new particle formation. So first question, what is new particle formation? So, or aerosol nucleation. So nucleation is a gas to particle conversion process in which you have a new particles formed directly from the gas phase. So in other words, when same or different molecules aggregate to form a new particle, to form new particles in the atmosphere, but the aerosol nucleation itself decreases the enthalpy and entropy of the thermodynamic systems. So there exists a Gibbs free energy barrier. So that needs to overcome in order for a phase transition, what we call as a gas to particle conversion. Okay, so that delta G is given by equation 1 here, and you see, as long as system is supersaturated, so you have L and S, as long as system is supersaturated, the first term will be negative, and that is the driving force for diffusion of vapor onto the particles. Whereas the second term is dependent on the particle size. Smaller the particle size, the surface energy of a smaller particle size will be much higher than the surface energy gained by the nucleation. As a result, there exists a barrier, and that prevents for a gas to partition into particle phase. That's what basically this delta G indicates. So in order for a particle to form and remain stable in the atmosphere and grow spontaneously, it has to overcome this energy barrier and reach to some radius, what we call as the critical particle radius. Once it crosses the critical particle radius, then the particle can eventually spontaneously grow in the atmosphere. So that is what basically the aerosol nucleation. Then question comes, what are the vapor which participate in aerosol nucleation? So we have what is called saturated vapor pressure. A higher saturated vapor pressure means a molecule will be, or substance will be more volatile, which means they will dissolve from the surface very easily. They will not stick back together. So in order to create a cluster, having maybe 10 or 15 different molecules, you need a compound with lowest possible saturated vapor pressure. So sulfuric acid has the lowest saturated vapor pressure among all other precursors that is well known to participate in nucleation, including water vapor. You can see it has very high saturated vapor pressure. So we believe that new particle formation or aerosol nucleation start with sulfuric acid, and then ammonia or amines condensation more contribute to the growth of these particles. There are also some of the vapors which are emitted mainly from biogenic sources, which are highly oxygenated molecules with extremely low volatility. They can also be involved in aerosol nucleation and growth, and they mainly come from the biogenic sources like forest. Then question comes, what are the different aerosol nucleation mechanisms? There are several mechanisms have been proposed in the literature so far. So we have a binary sulfuric acid water system where sulfuric acid and water molecules aggregate to form a cluster. This system is very well understood, but it works only in the upper troposphere or lower stratosphere. We have a ternary sulfuric acid water ammonia system, which pretty much works in the boundary layer, but this particular nucleation mechanism has been hampered by the limited laboratory measurements. And ammonia is here crucial because the ammonia condensation reduces the vapor pressure of sulfuric acid, and that makes ternary homogeneous nucleation prominent in case of a new particle formation. We have a ternary sulfuric acid water amines as well as sulfuric acid and organics. In addition to these, we have what is called ion-induced nucleation of sulfuric acid water. At surface, the ion source is from radioactive decay of materials, especially from the soils. But this particular nucleation mechanism works very well in the upper troposphere because you have a source of ions from galactic cosmic rays. But overall, if you see the contribution of ion-induced nucleation to the total, aerosol formation or aerosol formation rate, it turns out to be less than 10% or 15%. But the charged particles are much more stable than the neutral particle, and they can go rapidly in the atmosphere if they form. Okay, so these are the different mechanisms which are used or explained over the continental region. Over marine regions also, we have some of the species like iodic acid, methyl sulfonic acid. They can contribute to the aerosol nucleation or aerosol formation. Then what happens after aerosol nucleation? Okay, there are two possibilities because these clusters are very small, sub 3 nanometer, between 1 and 3 nanometer, that is 10 to the minus 9 meter. So there are two possibilities. Either these clusters are scavenged by pre-existing particles which are present in the atmosphere. So they are scavenged. So you have basically lost those newly formed particles. Or, so what we call as a coagulation loss. Or these smaller clusters can eventually grow to 3 nanometer and can also reach to even cesium sizes. So these are the two possibilities after the new particles forms in the atmosphere. So the picture on the right, what you see is the analogy between the competition of particle growth and the scavenging of pre-existing particles and a game of American football. So the red ones are coagulators, which basically nothing but the pre-existing particles, large pre-existing particles, and the blue ones are your condensators, those which will condense onto the newly formed particles. So there is a competition between the scavenging and the condensation growth, and what you see basically eventually a very small fraction actually reaches to sizes where it has a climatic relevance, that is cesium. So what is the new particle formation? So new particle formation nothing but the two-step process where the particle nucleation occurs and then those newly formed particles grow in the atmosphere at a larger sizes. And new particle formation, we say aerosols are ubiquitous. I also say new particle formation ubiquitous because it occurs everywhere, at the surface, above the surface, in cloud, out cloud flows, over the marine regions, forested, everywhere. And it is one of the, or rather I should say, it is the largest source of aerosol numbers to the terrestrial atmosphere. But when it comes to the mass, it contributes very little because this particle is very small. Okay. So then next, how do we detect new particle formation and characterize in the atmosphere? So detecting new particle formation is very easy, or rather I should say it's cheaper, much cheaper, but cost-wise. But if how to characterize, you need a range of instruments. So on the vertical axis, what you see, I have a size range from about 1 angstrom to 1 micrometer. So in order for characterize, you need a size information over this particular size range. Along y-axis, we have a time. So what we need is the measurements of gaseous molecules, including the oxidants as well. So we have sulfuric acid, VOCs, ammonia, and different oxidants. Those are measured usually by PTRMS, proton transfer mass spectrometer, or chemical ionization mass spectrometers. And the figure here shows the clusters 1 to 3 nanometer. That's where the nucleation occurs, initial steps. And these are usually measured with the nano condensation nucleus counter or neutral air ion spectrometer. Or we also have what is called chemical ionization atmospheric pressure induced top. That gives the chemical composition of these small clusters. And then of course the bigger size range from about 3 nanometer to about micrometer can be measured using the scanning mobility particle sizer or differential mobility particle sizer. We do have what is called the size dissolved chemical composition measurement by AMS TOF or ACSM also we can use it. Now what you see here is a new particle formation is essentially a daytime phenomena. It occurs after the sunrise, but there are also about 10 different sites across the globe where they have observed new particle formation during night time. Okay, but it's essentially a daytime phenomena. So what you see that after sunrise there is a huge particle burst. So this is diameter here, you have a time here, and the in color bar basically number of particles. So you have particle burst right after sunrise, and if you come here, these particles are growing over the time. So you can see there is a more diameter which is being plotted. So as the time increases, the more diameter is increasing. So it means that those newly formed particles are growing over the time. And this plot then looks like a what is called banana. So banana plots are idealization of new particle formation taking place in the atmosphere, or let me say it otherwise, aerosol nucleation and growth occurring in the atmosphere. Okay, so that is the kind of evidence of new particle formation. Now, if you see the range of instrument that I need to characterize, it's more than 200 million INR. Okay, so as a faculty, if you have to generate this much funding, it's not that easy. So that is why I'm saying it's computationally cost-wise, it's very expensive to characterize NPM. Now, what are the different characteristics that we look at? Mainly the frequency of occurrence of NPF, how frequently it occurs, that I need to know first. Then what is the strength of new particle formation? I can do that by knowing their formation rate and growth rates. Then atmospheric condition and synoptic condition and air mass history also influence new particle formation. So one has to characterize looking at what is influence of atmospheric and synoptic condition, and of course the chemical composition, which is something in Indian context especially very little known about it, and there are hardly any studies except one or two here and there. So that was my basically motivation, and what I said here, known unknowns, is because there are certain things which is known globally and even Indian context, but still unknowns because we do not have the process level understanding. If new particle formation, how it proceeds, and what are the different atmospheric condition under which it occurs or it inhibits. So NPF is the largest source of aerosol numbers and occurs throughout the terrestrial troposphere, but whether it contributes to aerosol mass or not, that is still questionable. Then NPF is expected to be less favored in polluted atmosphere than in clean atmosphere, because in polluted atmosphere you have large number of pre-existing particles, those basically scavenge the aerosol vapors. But in Indian context or even China or even developing nations, the highly polluted environments are becoming hotspot for new particle formation. So I'll be showing in following slides. New particle formation enhances cesium concentration in the troposphere by a factor of 0.5 to 11. But if you look at the uncertainty range, which is about 45 to 85%. Okay. So in order to quantify climate, what we look at is basically radiative forcing, by different climate drivers. And one of the climate driver is your aerosol effect, aerosols basically, or aerosol cloud interaction, which is the least understood process in the climate system. And the foundation in the uncertainty of aerosol cloud interaction mainly lies in the ambiguity of cesium production, which itself stems from the uncertainties in NPF, whether it could be a homogeneous nucleation or heterogeneous nucleation. The primary emissions, because as I said, there are strong spatiotemporal heterogeneity, and the growth rates, whether it's a SOA formation or CR formation. And SOA is something that has been largely unexplored in Indian context as well. So therefore, altogether, NPF has a critical importance for weather and climate studies. In Indian context, gas to particle conversion was first studied by exposing precursor gases to solar and nuclear radiation, and which dates back in 1970s. Work by VPN Ora and VPN Nair and KG Ora. But atmospheric NPF was unrecognized or recognized only recently. So in India, it was studied very sporadically, and the first atmospheric new particle formation was reported in 2005, not so long ago, while it has been extensively studied in US, China, or Europe. Precisely, there are only 30 articles published in entire Indian literature on new particle formation or atmospheric observation of new particle formation. So far, there is not even single study based on modeling efforts and the chamber studies, while it has been done extensively in Europe or US. So in Indian context, we have papers from urban, semi-urban, urban coastal, semi-rural, mountain remote background, and semi-rural, and also cruise-based observation. So this map just shows the background color is basically MODIS, AOD, and different sites from where new particle formation is reported. Different color is the type of site, and the numbers, basically the number of studies reported from each site. Okay, so you can see that there are only some 10 different sites from where new particle formation has been reported. Now the question comes, why studying atmospheric new particle formation in India? So the picture on the right, what you see here is number concentration, and along horizontal axis I have different types of events, new particle formation events, non-events, polluted days, and some other days which I could not characterize between these three. And what I have plotted is size segregated number concentration. So blue is sub 3 nanometer, orange is 10 to 25 nanometer, what we call as the nucleation mode particles. Yellow is 25 to 100 nanometer, that Atkin mode, and the violet is 100 to 514 or 1000 nanometer, that is basically your accumulation mode. So what you see, interestingly, if you look at the sub 3 nanometer particles, on all these event types you have very high concentration of sub 3 nanometer particles. That basically indicates that aerosol nucleation is not inhibited even at very high pre-existing aerosol concentration. Okay, that's one conclusion. Second, if you look at the, for example, Atkin mode particle concentration, you have more Atkin mode particles during NPP events than any other days, even the polluted days. Or even if you look at the accumulation mode also, you can see there are slightly higher during NPP event days than polluted days or non-event days, which basically trying to indicate that new particle formation can also contribute significantly to the total aerosol mass. Now, if you look at the picture on the right, this is the correlation between sub 3 nanometer particles and PM 2.5 concentration for Hyderabad, and the bottom is for the Beijing. In Hyderabad, what we see, there is a positive association. That's what I said. New particle formation is not inhibited under high pre-existing particles. But that's not what we observed. They observed in China, Beijing, where they clearly see that if the aerosol mass or pre-existing particle increases, the cluster mode concentration decreases. Okay, so it could be that we have a different climate types, and we altogether might have different processes that are driving new particle formation. Then next is we look at the frequency, how frequently new particle formation occurs in India. So the blue bars are NPP event days, the red bars are non-event days, the green ones are undefined events, and on vertical axis percentage of event days per month, on horizontal axis we have different months. This is Ranichori, Mahabaleshwar, and Mukteshwar. So you can see these are the mountain side, mountain background and mountain semilunar, where new particle formation occurred infrequently. Hyderabad, Delhi, or Trivandrum, these are urban or urban coastal, where new particle formation occur more commonly. Where if you look at the, let's say, Europe or USA, you will find exactly contradictory to this. They will have more events for the rural or semi-rural than the urban environment. Okay, so there are clearly differences between the Indian context and the US or European context. Then this is a paper which we collaborated with Professor Gunte in 2014. We had a measurements from semi-rural Gadanki location, and this is the only paper from low elevation rural site currently in India. Most of the studies are from urban location. Okay, and what we observed was infrequent occurrence of new particle formation in Gadanki. So these are some of the key processes that trigger new particle formation. One is precursor vapor source. What is the source? Like sulfuric acid, ammonia, amines. Then condensation sink, how much are the pre-existing particles, and the atmospheric condition, local to regional. So what you see here are different parameters. CS is nothing but the condensation sink, relative humidity, solar radiation, temperature, wind speed, wind direction. The blue line is for the NPF event days and the red one is for the non-event days, and these are the average diurnal variation. What you see in all these plots is there is no difference between NPF and non-event days for all these parameters. So the second and third basically are the same for NPF and non-event days, which means that it's the precursor that is lower probably in Gadanki, which basically inhibited new particle formation. That's what we actually see here. The SO2 concentration are very low compared to Kanpur, what we have in Kanpur or Delhi. So that was one of the conclusion. Then where do these particles come from? Okay, this is one of our study, recent study where we use the nano condensation nucleus counter. This is first and only available in India, which gives the aerosol size distribution in 1 to 3 or 4 nanometer, and we can get the formation rate of these clusters, J1 nanometer or J1.4 nanometer. So what I have plotted on x-axis is the formation rate of 1.4 nanometer. Along y-axis is the sub 3 nanometer number concentration, and in color you have sulfuric acid toxic concentration. So you see very nice positive correlation between among all these 3 parameters, which indicates that sulfuric acid played a role in aerosol nucleation. But was sulfuric acid enough for aerosol growth? No. So that's what I am showing here. So we had observed 2 types of events. One is this that you have already seen. You have burst of particles, and these particles grow over the time, and you can see the banana plot. So that is new particle formation. But other type where we see only the burst, even the strongest burst than this, but there is nothing in the SMPS data, which means that there are not enough vapors for those clusters to grow. So could be low volatile organic compound or unavailability of volatile organic compound that makes these kind of events. However, in Chennai we saw something different. This is again in collaboration with Professor Gunte, the data from Chennai, where we observed actually only 2 events during COVID-19 lockdown, and what we found that the sulfate concentration is more than 40% of the total mass, which is something unexpected. We usually find about 15 or 20%, less than 20%. But this was one of the event where we found very high sulfate concentration, and which was under the influence of sulfur plume from a power plant. And one of the other finding was these aerosols which formed during the this particular event had very high CCN activity, which basically indicate their cloud forming potential. So these results can help us to delineate anthropogenic influence on aerosol formation and the cloud perturbations. Similarly, we also did measurements at Hyderabad site during COVID-19 lockdown. So that's what you see here, the data from SMPS and data from nano condensation nucleus counter during the lockdown from 15 April till up to 31st May. And I was the one who used to go to lab every day to switch on my instruments while my students were at home. This is for the 2019 business as usual time period. You can clearly see notice the color contrast. So of course you had very low aerosol number concentrations, and during this particular time period the NPF frequency was 3-fold lower during COVID-19 lockdown. So what is this implication? So if you have a suppression of new particle formation, that could also dampen the aerosol's cooling effect. So what basically we need to do that is to understand air quality and the climate. These are completely 2 different entities, and how they interact and what are their feedbacks. That is what we need to understand. We can't just try to fix one, let's say air quality, cutting down the emissions like here we did, and we have a reduced frequency of NPF, which could dampen your aerosol cooling effect. Then you will impact the climate, right? So you have to understand both in how they interact each other and what are their feedbacks. This is another study and the only study available in Indian literature, where we used aerosol mass spectrometer, not to really understand the chemistry driving NPF, because it's not possible to do that with the aerosol mass spectrometers. But what we found there was, we found freshly oxidized hydrocarbon-like organic aerosols, mainly coming from the combustion generated primary aerosols. So that is nothing but the traffic. And when we looked at more into detail, we found that there were elevated signals of nitrogen containing compound like amines, methylamine and dimethylamine. And so that basically indicates that traffic is a source of amines and so on. Then of course, in terms of the climate point of view, what fraction that survives and grow to casein active sizes. Okay, so we use two different methodology. One is based on Pierce and Adam 2007 paper, and other is based on Kerman et al 2012 paper. And in the first paper, what we use is 50 nanometer and 100 nanometer particles as the proxies of CCN, and we try to calculate their survival probability against the source and the sink. So source is nothing but the condensation, and the sink is your condensation sink, coagulation sink. So it's nothing but the ratio of condensation growth and coagulation sink. And what we found that, especially at the Ranichori, the 60% particles that is surviving to 50 nanometer are survived to 100 nanometers. So by and large, 50% particles that are formed from new particle formation can survive to casein active sizes. Okay, and whether they really act as a casein or not, that depends upon the chemistry, the composition. Okay, not just the size. And if you look at here, we have calculated also increase in casein concentration and increase in absolute concentration and the percentage concentration. So we have a about 200% increase during the new particle formation events. Then question comes, when does new particle formation event occur? Okay, so this is the figure from one of our review paper, where you can see at x-axis you have a nucleation rate, y-axis you have growth rate, and different colors indicate the different site type, urban, semi-urban and so on, and the size of symbol indicate the condensation sink. So higher the condensation sink means you have large pre-existing particles. So ideally, new particle formation should be inhibited at higher condensation sink or higher pre-existing particles, which means also that you should have lower formation rate and lower growth rate, but which is not the case here. You can see Delhi, which has the highest condensation sink, which has the highest formation rate as well as highest growth rate. Okay, that is something again differs from the studies or observation reported in case of European sites. So what basically this indicates that is the balance between the precursor vapor concentration and the pre-existing particles decides when new particle formation will trigger in the atmosphere. So this is a very interesting plot. Yeah, Sachin would agree to that. Along x-axis you have condensation sink, and along y-axis you have growth rate, and blue is for Hyderabad and green and red for two different sites, and the symbols behind are for Hyderabad data points for October, November, December, January, February. Okay, so there is a study by Chu et al 2019 from China. What they observed that new particle formation occurs when this ratio is greater than 50. Okay, especially in case of polluted environment. But what we observe that new particle formation is more common when the ratio is less than 50. So when ratio is less than 50, which indicates that the atmosphere itself not polluted, it's rather moderately polluted. Okay, then how can you have a moderately polluted kind of condition in an urban environment where there are different sources? Okay, so to address this, what we did first was looked at the back trajectories. We just try to first understand the air mass history for nucleation days and non-nucleation days. The blue ones are the NPF days, red ones are the non-event days, and what you see that the source is not different. So source is doesn't matter whether they are coming from what source, it doesn't really matter. Okay, then next what we did was we looked at the altitude time variation of the air mass back trajectory, how they have traveled in the atmosphere, because source is doesn't affect, but as the air mass moves, how it has modified along the path. So this here it's for NPP event days and this is for non-event days. So what you see that for NPP event days, the air mass back trajectory coming from free troposphere and intruding into the boundary layer, whereas you don't see that for non-event days. For non-event days, air mass usually travels along the surface. So one would expect very high condensation sink or pre-existing particles for the non-event days. So we then looked at the vertical velocity. So positive value means the upward and negative means the downward. So you can see that on NPP event days, you have much stronger subsidence than non-event days. So we believe that the new particle formation occurs on the day where you have a subsidence and which somehow dilutes the atmosphere in an urban settings. And whereas in case of non-event days, you don't have that much stronger subsidence, which basically means you probably have more accumulation of pre-existing particles. There are also other hypotheses which have been reported by Clark et al., where they said that free troposphere acts as the reservoir for condensed vapors and can facilitate NPF. That is also possible, but of course we don't have measurement to prove that. For that you need aircraft measurements in order to say that if there are enough vapors in the free troposphere or not. Or yeah, so or mixing of contrasting air masses can also result microscopic fluctuation in thermodynamic properties, which can also create local supersaturation for precursor vapors. So these are the two hypotheses have been proposed earlier, and what we say that free troposphere intrusion results in planetary boundary dilution, reducing condensation sink, and that favors the new particle formation in an urban setting. So overall, there are several knowledge gaps in Indian context. I have just highlighted few of them here, and let me say that aerosol nucleation is a non-linear dynamic process, and the chemistry driving NPF in different atmospheric environments in Indian context has not been yet explored. What is then contribution of newly formed particles to cesium production and cloud forming potential? There are hardly one or two studies, looking at NPF and cesium linkages in Indian context, and even globally also there is not much work done on this particular topic. Then how do we quantify the relative contribution of VOCs in NPF and growth? That is something also unexplored in Indian context. Then the relative importance of NPF to haze formation and air quality. There is one paper I have not talked about here, but it's not really NPF or homogeneous nucleation, but what we observed in that Nature Geoscience paper is the heterogeneous nucleation, where primary vapors emitted from biomass burning are condensing onto the pre-existing particles and growing them to much larger sizes. As a result, what we have haze formation, and one of study by Professor Gunte also published in Nature Geoscience talks about the aerosol's role in the haze formation. We have been, putting our efforts for NPF studies in India for last 7 or 8 years. We have been working with national and international partners to develop adequate capacity for aerosol phenomenon and key process level understanding. Recently, we also conducted first international symposium on secondary aerosol formation and growth, Nano 2023. We also published, not really published, but yeah, we prepared the white paper and submitted to PSA, Principal Scientific Advisor, as well as Secretary MOES and Secretary SERB and DST. And I'm happy to see that there are participants from Nano Symposium here. Way forward in NPF studies for India, to develop adequate capacity for key aerosol process level studies and encourage synergy between observations and modeling. Then national and international collaboration for capacity building to determine aerosol effect on air quality, weather, climate over India. It could be multi-site, multi-institutional, multi-platform. It has to be continuous and long-term. So basically, in short, what we need is more and more observations at more and more places and environments in synergy with modeling efforts. So only observations will not really help to delineate all the anthropogenic influences on the climate. This is one of the review paper which published in 2022, and I have a animation of it. If you don't mind, it is about 4 minutes 50 seconds.
A complex mixture of gases contains a vast and intricate realm of minuscule particles called aerosols. Aerosols can range in size from a few nanometers to several micrometers. And this variability occurs due to a multitude of factors. One of the factors that impacts the size of aerosols is specific geographical location in which they exist. The size also depends on the prevailing weather conditions in different geographical locations. The source of air pollution is another crucial determinant of aerosol size variability. The aerosols emitted from these sources are directly released into the atmosphere and are known as primary aerosols. Anthropogenic emissions of precursor gases and aerosols can undergo physical or chemical transformation to form secondary aerosols. On the other hand, secondary aerosols can also be generated from scratch when gaseous precursors undergo nucleation to form new particles of nanometer sizes. When these particles grow and reach a critical size, they become active cloud condensation nuclei, which plays a crucial role in cloud formation and precipitation. The process is known as new particle formation, or NPF. Aerosol sizing instruments, such as the Scanning Mobility Particle Sizer, or SMPS, play a vital role in detecting NPF events. SMPS operates based on the principle of the mobility of a charged particle in an electric field. It allows scientists to measure and characterize aerosol particles based on their size and electrical charge. The SMPS technique is widely employed in atmospheric research and environmental monitoring to detect even ultrafine particles. The graph plotted using data from Scanning Mobility Particle Sizer exhibits a distinct curved shape, often referred to as the banana plot. The banana plot is a characteristic feature in the graph, showcasing the evolution of particle sizes over time during NPF events. Observations of the formation and growth of new atmospheric aerosol particles have been documented mostly in Europe, China, and the US. However, such observations are scarce in India. A review of total of 25 published studies in India on NPF provided valuable insights into various aspects of NPF events, including the factors that influence and regulate NPF. These studies were conducted in different atmospheric environments such as urban, semi-urban, urban coastal, semi-rural, mountain remote, mountain background, mountain semi-rural, and cruise. For example, studies show that new particle formation took place during periods of heightened solar radiation and less in the absence of sunlight when the intensity of solar energy is its least. Another study showed NPF occurrence to be higher in urban areas compared to rural and mountain background sites. In a significant breakthrough, a study conducted in India established likelihood of newly formed particles surviving and growing to sizes that make them cloud condensation nuclei, which is typically above 50 to 100 nanometers. In India, most studies have focused on size distribution of aerosols, but underlying chemistry is still unknown. Also, the precise contribution of newly formed particles to cloud condensation nuclei production and their potential for cloud formation remains uncertain. Further investigation is essential to unravel the intricacies of this process. Another aspect of new particle formation that requires further assessment is the relative contribution of volatile organic compounds to new particle formation. And most importantly, the role of NPF in haze formation requires further research. In order to unravel the unexplored realm of new particle formation, it is crucial to foster collaboration and commitment among researchers, institutions, and stakeholders. As we venture into this uncharted territory, unified efforts will lead to groundbreaking discoveries, illuminating new paths in atmospheric science. This shall enable us to address the intricate interactions between aerosols, clouds, and the Earth's climate system, which is still to be fully comprehended and plays a vital role in shaping our understanding of climate change.
So this was probably a short summary of my entire talk.
Our atmosphere.
Yeah, so with that, I just want to acknowledge first the research funding that I received from different funding agencies, BSB, and of course University of Hyderabad, and of course my collaborators and my students who has been, played a key role in the work that I have done, mainly the Matthew who has been working on new particle formation. With that, thank you so much for your kind attention, and I'll be happy to take questions.
We still have time for some questions, but I'll start with why this thing first. So just want to ask about this closure, right? When you have the BOC, for example, and then the nucleation is happening. Now, I just want to have your view about like the closure which we want to attain. So let's suppose if I have a PTRMS and then this instrument can measure the nucleation, for example, right? And then at the same time, if I'm sampling the aerosol and I take it into the QCM and then do this photolysis experiment and take the output of the QCM to the PTRMS. So do you believe that it is a correct sequence to do that to obtain the closure, because what will it form through, and then really check that whether it was true, because I can still calculate the yield, right?
Yeah.
So that sounds like a correct way of
I think pretty much to me. Yeah.
You operate that instrument which you
Yeah.
1, 2, 3, and then I operate it with the PTRMS.
Yeah.
And they keep sampling continuously. So I hope Shalina is listening to it. So,
But you have to sample for maybe 4 or 5 hours minimum.
No, we will do it continuously, because because you can't predict the event, right?
Exactly.
So you're sampling for 1 day, 2 days,
Yeah,
5 days, 10 days.
exactly.
And then notice that whenever there is an event, so pull out that data from the PTRMS, and then you know that you can simply go back and do this Kava makeup model which we have not modified to calculate the yield of the SOA, along with the nucleation. And then those aerosols which we have sampled, put it on a QCM, put the UV light, and take that output to the PTRMS. So that closure, I think, would really
it is possible. You just have to run 24/7.
Yeah, we will do that anyhow. I mean, the sampling, they do it anyhow.
At least to get a one event, if you know when they are more frequent.
Right. Just one more thing is that maybe you touched it, but I missed it upon, is that when we talk about the different VOCs for the formation of the secondary particles, for example, I do believe that the VOCs which are the long chain compound, they are probably the first one to really form the SOA, right?
Yes,
for example, isoprene,
because they are the one who are highly oxygenated.
They have the highest. But does it then also happen that if you do this photolysis effect, they would be the first one to really kind of because in some complicated environment?
No, I probably don't think so, because if those compounds goes into the cluster, what else you have is a condensation. I mean, nucleation is just what happens below 3 nanometer. Once you have cluster which is stable, which is growing, so that cluster may be made up of those highly oxygenated molecules. What else you have is just a condensation.
Yeah,
that could be anything.
Is because that when we talk about the secondary particle formation, there is a huge difference between their CCN activity. I mean, what we see from our lunar observation, that the secondary which are formed to be biogenic, they are really very bad CCN, right? Because of this solubility limitation. Whereas, let's say, suppose if you have an aromatic or anthropogenic VOCs, from which what we saw forms, they have a better CCN.
But how do you say that they are bad? Do you know the composition?
Because you clearly see the solubility limitation.
Okay. Based on that.
This nature communication paper also said
Okay.
Biogenically derived SOAs, they undergo this very strong phase transition.
Okay.
Right? When they go under the phase transition, there is a strong solubility limitation. That's the reason we want to measure it in the subsaturated and supersaturated. So, do you think that it is also a good approach to now delineate that the CCN activity of the SOA formed between a biogenic use and anthropogenic use? I could see that there could be a difference of, I don't know, maybe a factor of 3 in their CCN activity.
Could be, but you first have to segregate the biogenic and anthropogenic component.
I mean,
if you could do that, then I think it's possible.
I think the PRMS coming up and CCN running through, and then with the QCM, I think you could probably be able to. The QCM, we fairly know now the derivations for the biogenic, not chemically. But we also have an ACSM which we could look into.
Yes.
Few million rupees.
Yes.
Okay.
It's doable, definitely. Yeah, please.
So I understand that you are reporting this urban regions MTF is getting more. You have some hypothesis also.
Yes. No, I'm not saying that it is getting more. I mean, they are becoming a hotspot. In any sense, what I'm saying is, as I mentioned, we have measurement from only one low elevation rural site, that is Gadanki. And now we are working on the second, Mahbub Nagar, where also we find infrequent new particle formation. The problem is we have measurements only and only from urban environments. And what I see, there is new particle formation occurs commonly. So that is the first thing. See, if we do more and more rural environment measurements, then probably we'll have a much clearer picture. And the hypothesis you are referring to, that is possible in urban environment under the high pressure or subsidence.
No, that slide, Manichari was there,
Hmm.
was there.
Yeah.
3 rural and 3 urban.
Yes.
Compared to European, it's the
Yes.
other way around.
Other way around. Exactly.
What is your hypothesis?
It's very difficult to answer that question because if you remember the picture I showed where J versus growth rate, there itself is contradict to what they observed in Europe, right? So it's because if you take anthropogenic activity, biomass burning, it does not emit the aerosols but also precursors in the same quantity. So it's a balance between them that decide when new particle formation is triggered under given atmospheric condition and synoptic condition also.
The reasons could be that, what I believe is that when you have the emission of the precursors and particles, right, from any sort of a burning, then in the beginning that these particles are very small. Right? So being these small particles, it is still a very small condensation signal. So one need to probably add, so you showed this one of the figures that this is what Andy and always says that why it doesn't happen in Amazon, because you already have this biomass.
Amazon there is different mechanism. Isoprene.
Biomass burning, most of the time they did observe the new particle formation, right? Not in Amazon but in because what they believe along with the precursors, the particles are not undergone the transformation and aging. The condensation sink is so low that it could immediately be triggered. So
and that actually reminds me, in Amazon you have very low SO2 and you have very high isoprene. Isoprene suppresses new particle formation. If you have low SO2, new particle formation will not occur. And the study we are referring to that from Europe or USA, they are mostly from mid latitude, where you have a lot of pine trees. And when they call it rural environment, it's mainly vegetated. If you have a lot of monoterpenes, then you will have definitely new particle formation. So that is also another distinct difference between the Indian continent and the European continent.
I think monoterpene has even a higher yield than isoprene.
Yes.
In that case, Manichari or Mukteshwar.
I am not sure about those sites, how densely vegetated. And
the first line.
No, but the point is that you still have the very high condensation in there, because our rural is not really rural, right? So for example, what we found during lockdown, right? Even in urban area, despite having a very low condensation, you get a high growth rate. So what it probably does, the probability of gas to particle conversion is high, and then comes the growth. So that's possible mechanism.
And here you have new particle formation only when your boundary layer above the site altitude.
Exactly.
Otherwise, no. 90% times. I wouldn't say 100%, but 90% times. Only when the boundary layer height above the
Mahabaleshwar, I don't even really. What is the particle concentration in Mahabaleshwar? Like 1,500, 2,500?
No, more.
Yeah,
you have a lot more actually. 6,007 because you have a lot of traffic there. Vehicular emissions.
It is in high altitude.
It's a semi-rural, that's what we call.
Yeah,
mountain semi-rural.
But then again in Munnar, for example, during this monsoon, we never found, right? We never found any new particle formation.
Monsoon you will not. Definitely not.
But that's the hypothesis is like if you have a densely vegetated area and then
Summer.
the sun is out.
Exactly.
The sun is out for a longer period as you see. Right? We probably had something, but it never happened. Right? So
This time we tried in Manali also.
We did not see.
Same instrument.
Yeah, with the same no, not same SMPS.
SMPS,
We did not see hardly one event, I think, right?
Not
Not even one.
Trivandrum is also an anomaly, I will believe.
Trivandrum is also anomaly, or it could be a land sea breeze influence. I don't know actually. It's very difficult. The data.
There also.
Chennai, in fact, then we found.
Yeah.
I mean, after the lockdown, there is a series of.
It's very grey area. You just need a measurement.
Not grey, but then I think it is big. I mean, what it could be is that this kind of a distinction will at least make us think that what is different.
Yeah.
I mean, your distinction is not grey, right? But this closure is very important, right? Like you have this instrument which, if you could run it with the VTR, back calculate that will help us.
Yes.
Second is about that subsidence. When we are talking about subsidence, do you mean horizontally calm conditions?
Sort of. I don't know actually. I have not checked, but sort of. Because when I'm saying subsidence, I'm saying that regionally there is a high pressure system. So horizontally there will be calm condition, much stable atmosphere.
I think the only atmosphere is stable. We don't know if the advection is happening.
Yeah.
One thing to check is that in Hyderabad or such urban centers, a lot of pollution will be trapped.
Yes.
So when we are saying that it will come down and dilute,
Yes.
so there will be a competing effect.
Exactly. Yeah, that is also possible. Yeah, that's a good point.
Yeah, but then it will, if that mixing is like, it's not only the subsidy, but it's always mixing, right? In some cases, you have seen that when you, like in China, this Gao et al. Famous PNS paper, right? It forms and then immediately goes on increasing. So you say that subsidence is both way around.
In US also they have observed actually new particle formation under high pressure system. They have observed under subsidence.
So, I mean, what we are looking into the lunar data now, whatever the results which we found. So, I mean, we are working on the data, very preliminary assumption what we have. We probably saw that the new particle formation happening above the boundary layer and then the mixing is happening.
Okay.
So now this,
that is Clark hypothesis.
Yeah, so that is what exactly we are seeing now, that these guys are doing the modeling at increased growth. So we see that in the evening that way, it is not in the morning. Every few events at 5 o'clock, you saw a very strong burst of the particles.
Right.
I mean, not really as a banana shape, but a very strong piece, out of magnitude.
Yeah.
So then we know that if this precursor playing the three players, but it's obviously happening above the boundary layer and then mixing it down. I mean, it has either happened there and then mixing it down.
Yes.
We are getting close to that hypothesis.
Okay.
So, it was very nice to have one more.
Yeah.
So, lastly, the PM relation. There also, it's only with 3 nanometer particles.
There are only few data points. Green one, right? That's I know.
No,
so,
not in that sense.
Okay.
We have to be careful.
Yes, correct. It's just because there are 3 different inversion techniques to invert the size distribution from PSM data. So we use the best one. As a result, we have to throw out a lot of data points.
And their range is also very different from ours.
Yes, the range is also very different from us. Yeah.
But this is also a curious.
And this is only for, I'm showing for sub 3 nanometer. I am not showing here, but we do have a same relation for nucleation mode particles, where we have a lot of data points. We still see positive, but in Beijing they see negative.
No, but what is the problem here, that the other gray point you have is from the filter measurement or from
it's PM 2.5 is from filter measurement.
And gray is from filter measurement.
Yeah. No.
Maybe the best would be if you have an SMPS measurement, assume 1.1 density and convert it to the mass. Then you can probably extrapolate. That's what generally we do when we normalize it. Right?
But SMPS will go only up to 1 micrometer, right? What
You
about?
can say that PM1 is from PM 2.5. It doesn't matter. It's just a mass. You want to show that whether it is contributing or not.
But you may have a lot of dust particle around that may scavenge these clusters.
It's okay. At least just convert it. This one is Gao et al. Also as well.
Yes.
Talk about PM1, convert it to the mass with 1.1 density.
Yeah, that can be also done.
This 1 to 3 nanometer is very important to start with.
Yes.
Very
Yes.
More questions?
Sir, in Indian context, modeling is not done on
No.
So, what
I-
might be the main reason people are not exploring that part?
No, first, why there are no more than 30 papers, right? Based on observations, while almost every lab across India has got SMPs. How many SMPs? Probably there are hundreds of SMPs across India. So I don't know why. We tried actually one paper using aerosol microphysical box model. Unfortunately, we could not publish that. And I don't see there is anyone who is working. There is one colleague at VRC, Dr. Anand, who has been doing some modeling, but he's not really looking into atmospheric point of view. I think it's mainly based on some technological innovation or laboratory based experiments. But yeah, there are people who are doing modeling, but not from ambient measurements point of view.
We are also thinking to go with modeling of new particles.
Yeah. The one other reason could be you need a lot of data also. You see, right, 200 million. You need all those measurements because whatever modeling you do, you need to validate your model, right? If you do not have a measurement, you cannot validate your model. So that could be another reasons why people have not been looking into it.
And emission uncertainty might be a reason because we are using like 2015 at the data till now for modeling purposes.
Yeah.
So will that be a
I think that is known, right? Everybody knows there will be some uncertainties because of emission inventory and so on. So I don't think that is the reason people are not doing NPF modeling or microphysics modeling. Or could be, I don't know, I'm not a really modeler, so I may not.
What?
Modeling of nucleation. There are box models,
There
but
are this part MC and then there are multiple box models. So I was wondering that if you are talking about the implementing that into the global climate model or the modeling of the NPF events itself.
modeling of NPF events?
There are models, this part MC and then there are these creation models.
there are box models. Yeah. There are box models or there are NPF
They
explicit.
don't really try to look into the growth or other things. They first try to look at the yield of conversion of the VOCs into the particles. There are multiple models like that.
But definitely, this is something that can be explored. Has to be explored.
It's also very expensive.
Yeah, that is also there.
Now
Yeah.
only computational power.
Yes.
There is something which is called as a work NPF also. There is a
NPF explicit work.
Yeah.
There is one paper on
Work
that.
NPF also.
But it has a lot of issues also. There is one paper, but yeah, there are a lot of uncertainties.
It's too far.
Yes.
Yes.
Sir, for someone who is new to the subject of atmospheric and climate science, on what for land, air, or water, what more focus should be on for someone new?
I would say land because it's easy to access. Water is not easy to access. So I would go the place where it can be easily accessible first.
And then the processes are probably more complex on the land.
Than the marine regions. Yes. Marine region it will be much simpler processes, but it's not accessible.
What was the third? Land, air, and water.
But, yeah. Here also you can do only surface based measurements, even if you are looking at the ambient air. If you want to do, in the troposphere, you need a balloon or aircraft or something like that. Yeah.
Any more questions?
If you see the primary emissions, of course they are decreasing with altitude. But if you just take the nucleation, no, that's what I'm telling. If you look at the primary aerosols, of course sources are at the surface. So as you move away from the surface, concentration will decrease. But if you take into account secondary aerosols, then you pretty much have constant or even the increasing. So it's not just near the surface, that mainly comes from the primary emission at the surface. The secondary can give aerosols even at higher levels, above the surface, well above the surface, entire troposphere.
They have NPF didn't do any contribution in the
Contribution into?
convection.
I mentioned that you have a new particle formation occurring in cloud outflows. how does it occur? Because there is a lot of emission at the surface. During convective activity, those precursors are taken aloft, and there you can have a new particle formation. So of course, you will not have any precursor at higher levels, right? So the convection are the ones which can pick up lot of precursor from the surface and take higher up in the atmosphere.
The better perspective is these small particles can go into 100 nanometer.
Yeah,
That can get activated much higher.
much higher already. Yes, yes, yes. Thanks. Yeah. Good. Okay.
All right. There are no more questions. Then thanks, Vijay, for this